My name is I'm from the University of Kassel in Germany, and today the talk will be about the configuration of forces in material space and their use as crack deflection indicators and crack loading quantities for three-dimensional crack growth simulations. So as you may know, crack problems are often evaluated using two-dimensional boundary value problems, employing solutions of stresses and strains to calculate loading quantities and crack deflection angles. So one of the criteria for the calculation of crack deflection is the J integral criterion. This can either be used for materials with isotropic material behavior. Then the crack deflection angle only depends on the J integral vector and can be derived from its components. But the criterion can also be formulated for anisotropic material behavior. In that case, it's a bit more complicated to calculate the crack deflection angle, and it is in this case dependent on the energy release, which depends on the angle itself and also the crack resistance, which depends on the angle. And on the right hand side, we see some comparison of experimental crack path and simulated crack paths for an anisotropic material. It's a rolled aluminum plate. And what we see is that the resulting crack paths strongly depend on the choice of this value chi. And this value chi is the ratio of orthotropic fracture toughness, which depends on the fracture toughness in the transversal direction and the fracture toughness in the rolling direction of this plate. When we choose the right value for chi, which was also measured in the experiment, then we obtain the correct crack path, and the simulation perfectly meets the experiment. So this also works this works quite good for two-dimensional problems, but it can also be of interest to observe three-dimensional crack growth behavior. For example, when we want to observe curvature of the crack front to mode 1 loading, or crack deflection due to mixed mode 1-2 loading, or also the twisting of the crack front due to mixed mode 1-3 loading. And normally those calculations are based on, for example, equivalent domain integral formulations or interaction integrals. But the objective of this work is now to do this calculations based on configurational forces, respectively J integral vectors. So therefore, we need a crack deflection criterion for three-dimensional cases, and we assume that the crack propagates along the direction where the potential energy reaches a minimum value with respect to our crack deflection angles that we want to calculate. And this means that the potential, where the potential energy has to reach a minimum value, means that projection of the J integral vector on the crack propagation direction has to reach maximum value. From this condition, we can calculate our crack deflection angles, which depend on the components of the three-dimensional J integral vector that we have to calculate. So we have those two angles, phi and psi, which are calculated, as you can see here. Therefore, we need J integral vectors that we have to calculate for our boundary value problems. And normally, in the two-dimensional cases, they are calculated from this contour evaluation, where you calculate this integral, which consists of the shell tensor and the outward normal vector to the contour, and some terms regarding body forces. When we now shrink this contour towards 0, that it's quite a major crack tip. We can use this formulation to calculate a J integral vector at crack tip. This is fine for two-dimensional cases, but it doesn't work that easy for three-dimensional cases. There we can use the configuration of forces in material space, which are, when we have a look at the crack tip, equivalent to the negative of the J integral vector. So the idea behind this configuration of forces is that they act as a defect driving force. So when we have a look at a control volume projected to a load, then a force arises, a thermodynamical force that acts as a drag or as a defect driving force. This defect driving force is also calculated in this material space, where we have a Shelby's tensor Q, which consists of the strain energy density, the stresses, and the displacement or gradient of displacement. And with the Shelby tensor, one can formulate a conservation law of material space, which you can see here. And from this conservation law, we can then calculate the configurational force by this integral equation here, with an area integral and a volume integral. Numerically, those configuration forces are calculated from a weak formulation of this conservation law I showed you before, in terms of the finite element calculations. This was proposed by Rose et al. And Müller et al. In the year 2002. And what we do here is that the conservation law is multiplied with a test function integrated over volume that has to equal 0 then for the volume. And the idea is now that these test functions are discretized by the isoparametrical concept, so that we have the interpolation functions of the finite element method and discrete values for those values b. And from that we can derive the configurational force for each node I and each element E of a finite element mesh. And they get assembled to nodal configuration forces by summing up all the contributions of all adjacent elements to an node I of the element of the finite element mesh. From configuration forces, we can then calculate a pointwise J integral when we apply it to cracks in the finite element mesh. So we have these configuration forces at one point of the crack front. This should be a point P, or this is here as a point P, and we divide it by this term here, which is the interpolation function for that point integrated over a specific length, which is the element edge length at the crack front. So the problem with this formulation is that we employ local stresses and strains to calculate the configuration forces, and that means that we have quite inaccurate values for the configuration force when we want to calculate them at the crack tip, because there we have inaccurate solutions of stresses and strains. This is an example calculation for the configuration forces for smaller unmode 1 loading, and we see that the theory of the configuration forces says we should only have a contribution directly at the crack tip and also some on the crack faces. But what happens is that we also have contributions in the vicinity of the crack tip that should not be there, so there are quite unphysical, what we call them unphysical contributions due to the numerical inaccuracy. Yeah, we have to deal with that, and the idea is that because these forces should not be there, they have to be taken into account for the correct solution of the configuration force at the crack tip. So we find an area around the crack tip or the crack front, respectively, for three-dimensional cases, where we sum up all the unphysical contributions that should not be there to calculate an improved value of the configuration force, and with that an improved J integral vector. So this is what we do there. We have the initial calculation that we call F, which is the calculation at the crack tip, so this is crack 1. And we sum up the unphysical contributions in this area and also the unphysical contributions that appear on the crack faces. We implemented this into a post processor, which is working together with Abacus, and performed some crack loading analysis. This is the model I use. This is quite simple academic model. Just this, just this easy body under a pure mode 1 loading. The mode 2 part is neglected here. And we calculate this with two different meshes. So at first I will show you the results for a tetrahedral meshing. Like it's quite coarse mesh, just 50,000 elements. This is the side view of the meshing, where you see the cracked face here, the supporting system, and this is the top view of the mesh, where we have the crack here and you see the cracked front there. What we do is we calculate J-integral values for each one of the nodes of the mesh along the cracked front. So on the other side we see the initial value, so the initial calculation of the J-integral vector from our post processor, and those are compared to reference values that we obtained by using Abacus. That's the equivalent to main integral, this is solved here. And we compare the J1 because this is the important quantity for pure mode 1 loading. What we see is that the initial values have a quite big deviation from the reference values. So the red one is the reference value, and these are our calculations, with an average of about 12 or 13% deviation. Then we perform our improvement scheme. So for each point along the crack front, we choose a vicinity where we sum up all those forces, so all the contributions from the unphysical contributions to the initial values. And then we see that the results now come quite close to the reference value. So in total we have a mean deviation from the reference value that's about 2.3%. I think this fits quite well. We also performed these calculations for the hexahedral meshing. This, also quite coarse mesh, but also with the same element sizes as in the tetrahedral case. Same model, also the mesh that's seen from the side, the mesh that's seen from the top. And now we also compare our calculations to the reference solution that was obtained by Abacus. And here we also see that we have, without any improvements, we have a quite big deviation. Its mean value is about 10%. But we also see that some values fit quite good. But I think that's just because of the structured mesh, because it's quite different to have an unstructured mesh for this easy specimen. And here the calculations were quite good at each second node. But then we now again perform our improvement scheme, sum up all those contributions, and we see that we have perfectly fitting values to our reference curve, which have an average of 0.01% deviation, which I think is very good. So I will now come to my conclusion. It's quite short. So the topic was the efficient, accurate calculation of those three-dimensional configurational forces. We implemented a post-processor that calculates quite good J-integral vectors, respectively, or configurational force vectors, respectively, for three-dimensional crack fronts. And we also performed some improvements on the numerical accuracy, because due to the local approach, we had quite big deviations in our initial calculations. So thank you very much for your attention.